Hello. Today we're going to talk about something called Big O notation. If you read up about it in Wikipedia, Big O notation is a way that we describe how our algorithms perform. This is a common thing for computer science. If you look up Big O notation data structures, this is a great website here. The Big O cheat sheet, also very good. What we're going to see is basically this is a way of analyzing the cost complexity of different data structures. So the only data structure we've looked at so far is the array. We made a big deal about arrays versus lists, but we're going to come back and talk more about these, what all these different types of lists mean once we get into those next. But let's look at the Big O notation for an array. So all that Big O means is we look at our data structure, for instance, an array, and we are concerned about two things. The time complexity and the space complexity. The time complexity just means how long does this operation take, and the space complexity means how much space do we need to have on our computer. Both of these depend on how many things you have in your list. So if we look at the perhaps the simplest thing, if we have an array and we want to know how much space this is going to take in our program, like memory space, like RAM, when the program is actually executing. This says, the way you read this notation is you say it has a Big O space complexity of n. And what that means is, for an array, n it represents the number of things in the array. So what a Big O of n means is the worst space that this thing is ever going to take up is basically it's going to scale with how many things you have in the array. So n just means that if you have an array with one thing in it, you might take up 1 megabyte of RAM. And if you have an array with 10 things in it, you might take up 10 megabytes of RAM. If you have an array with 100 things in it, you would take up 100 megabytes of RAM. So the n means that there's a one-to-one comparison between how many things are in the array and how much space you're going to take. Now, if we look at this column, the space complexity is pretty much the same for all of these data structures, which means that the data structures all pretty much just grow linearly with respect to how many things you have in them. This one looks special, but we're going to ignore that. So let's look at the time complexity. And let's ignore the average column for now. We're just going to look at the worst case. So if you have an array and you're trying to either access things in it, or search for something, or add something, or delete something, it turns out that there's actually different time complexities for those. So here we have another notation. The two options here are Big O of 1 or Big O of n. So what this means is if you have a Big O of n, it means that the time it's going to take to search through things in your array is going to scale according to how many things are in the array. So if there are n things in the array, we're going to say, well, the worst case scenario for searching is it's going to take about Big O of n time. So if you have one thing in the array, it might take 1 second to look for it. If you have 100 things in the array, it's going to take 100 seconds to look for it. And it's going to scale with a factor of n. So search and insert and delete in an array, what we can see is the worst case is that this operation takes as much time to do as there are as many things in the array. Now let's think about that for a second. So with the search operation, if we have an array, let's consider search, insert, and delete. We say these are all O of n. And let's see. So if we have an array that is this big, and let's say this is 100, versus an array that's maybe 50, and an array over here that, let's say this has 10 things in it. So n represents the number of things in the array. And we're curious about how long it would take to search for something. So we want to know about searching. And we want to know about inserting something and deleting something. So I just write insert and delete. So, if we're going to search for something, well, what's the normal way that we search for something? We normally say for I, and we go between 0 all the way up to n, the length of the array. So when we're searching for something in the array, we generally make a for loop that goes from I, from 0 all the way to the end of the array. So if we're searching for something, that means that we have to observe every single thing in the array. We just have to move through it, and we have to look. Now, one thing that Big O says is maybe we could have gotten lucky, and the thing we were looking at actually appeared right here. Or maybe we could have gotten lucky, and it could have appeared over here. Or maybe we could have been a little bit less lucky, and it might have appeared all the way down here at the end of the array. Well, this is why when we look at the table, Big O notation does not represent, normally people don't talk about the best case or the average case. What Big O represents is what is the worst possible time that this thing could take for this to happen. So in this case, even though we might be searching for something in the beginning, or we might be searching for something in the middle of the array, the absolute worst case is that that thing is going to be at the end of the array. And so for the worst case of search, it's going to take a big O of, it's going to make an amount of time which is proportional to the number of things in the array. So n represents the number of things in the array, and the big O notation just it's just a way of saying we're saying that the worst case is scales according to n here. Now let's consider the insert. Well, if we wanted to insert something at a specific element in the array, remember that if we are trying to insert something maybe here, we actually have to scoot everything else over. So when we are inserting in an array, we might have to scoot everything over to make room for it. Now again, maybe we would be trying to insert something here at the end of the array, and we might only just have to do a few scoots. But the worst case scenario for inserting something from an array is we might have to scoot every other thing over to make room for it. So we say that the big O, when we say big O, we mean the worst case scenario for inserting something in an array. Well, the worst case scenario is we might have to move n things, because n, again, represents either there's 10 things or 50 things or 100, but this notation is a way of saying, depending on the size of your array, the time taken, the worst case time taken to insert something is going to be n. So we can see that the best algorithm we have for insertion, the worst case scenario is we might have to put something in there and it might move over. The same thing is going to be for delete. Delete is very much the opposite of insert. If we're trying to remove something from an array, well, we're going to have to scoot all these other things back to fill that place. So we can see that the worst case scenario is if we deleted something from an array, it might take us, we might have to do something for the entire size of the array. There is one place where arrays actually have a great runtime, and that is in access. So by access, we mean if we're ever trying to say, give me the thing at A at I to read something, it turns out that the arrays actually have a very quick access. They actually have it, we call this O of 1. So what O of 1 means is it means it's constant time. And the reason why it's constant is we're saying that no matter how many things are in the array, it doesn't matter if your array has 10 things or 50 things or 100 things or even a million things, one property of arrays is that if you simply want to access something, if you just want to ask, what is the thing right here, access A at this spot, it turns out that arrays are very quick at this. With arrays here, it doesn't matter how big the array is. You could ask for something anywhere, and the computer is going to take a constant amount of time. It means they're going to take the same amount of time to retrieve what you're asking, whether you ask for it in the middle, or the end, or the beginning. And so we actually write that as O of 1. All that O of 1 means is that it does not rely on the size of the array. So here when we say O of n, that means that this scales, the time it takes scales with how long the array is. When we say O of 1, what that means is it doesn't matter how many things are in the array, this thing is always going to take just some amount of time, some constant amount of time. There are other big O notations that are very common. Here's a quick picture of other common ones. So we've seen O of n here, which means that you're basically going to do something for every single thing in an array. And we've seen constant O of 1 here. This means that no matter how many things you have, so this on the bottom means basically how many things are there, and this means how long does that take. So you can see here that if we look at just the O of n line, well, if you have few things in your array, it's not going to take much time. And the more things that you have in your array, the longer it takes. And it goes up in a curve like this. Or rather, this is just a straight line. So when you have O of 1, you can see that the time something is going to take is proportional to how many things are in your array. The O of 1 line down here means it doesn't matter how many things are in your array. In fact, it doesn't matter if you have very little things or if you have very many things. What this means is it's going to take the same amount of time no matter how many things are in your array.